One of my personal issues with the way a lot of calculus is taught is that it is taught as an extension of algebra. It is taught as symbol manipulation. And while I agree that that works, to me, the bigger part of calculus is thinking of it as an extension of geometry, and thus as an idea of visuals and shapes and areas. We kept talking about the area under a curve. I don't want you to do this integral. I know you can do this integral. Sketch it. What does it represent as an area? What's the picture you get? So I think of the graph of y equals x squared, and I see this piece of a parabola, and I know I only need that piece because I'm only working between 0 and 1. But when I write out this integral, I picture drawing a vertical line that ends at x equals 1, and I think of this region. At the same time, I have a picture in my head of the Riemann sum we did. And when we did the Riemann sum, we did a bunch of those little rectangles, right? And the rectangles had a little width, delta x, and they had a height. But I'm going to think of that height as going from the curve x squared to the bottom, the x-axis, right? What's the equation for the x-axis? There's some equation for that line. Every horizontal line has the same equation. What is the equation for any horizontal line? Y equals a constant. What's the constant for the x-axis? What's the height? Y equals what here? So I can think of the height of this rectangle as x squared, but I can also think of the height of this rectangle as x squared minus 0. See how I get that literal behavior of a rectangle, height times width? And the height is the difference in the y values. My choice was to use the x-axis. We defined area under a curve. Well, whatever it is when it lands next, squash it. I understand. There's no reason I couldn't use something else. Let's do the same thing. I promise it's just a bug. When it lands, we'll kill it. Let's do this same idea. For the line y equals x. Promise, whatever it is, when it lands. It's on the ground, right? Move that. Somebody find this pen. Missed it. There it goes. The top will land above your head. Let's take a pause. Keep an eye on it. Right. Well, I can't get the same. We'll have to go with the eyeballs again. We'll kill it eventually. Somebody draw me another picture. Valid attempt, Jordan. Sorry we weren't successful. What's my other picture look like here? This one's even easier. What's this graph? Just a straight line. And it goes through the point 0, 0, and it goes through the point 1, 1, just like this did. So this is our region. So a little rectangle in this case is going to look like this. And again, I see I'd go for the top, the line y equals x, to the bottom, the x-axis. Okay. Visually, consider both of those curves at the same time. So I have the line y equals x, and I have the parabola y equals x squared. And I have a region now between these two curves, bounded by the curves themselves. I'm not considering the x-axis anymore. I'm considering just that slice. Technically, I would call this kind of a lune. It's a round side and a straight side, a crescent of a piece. Technically, a lune is the section between two circles. Similar idea. How would I find the area of this thing? I could think of overlaying my two pictures. Let's draw this vertical line. That hits 1. 1, because I know that x is equal to x squared. Means x minus x squared is 0. Either x is 0 or x is 1. That's where those two curves intersect. But that means that this region has a boundary on the left at 1, a boundary on the right, a boundary on the left at 0, boundary on the right at 1. And this, all right already, geez. This outside picture is this triangle. Hey, wait a second. This triangle right here, that's this triangle. And this area, that's this shape. I want the area that's in the triangle that's not in this shape. What do I do? What arithmetic would I do? I have a big piece. I want to do what with the small piece? I want to take it out. I want to subtract it. So if I were thinking just geometrically, I could say what I want is the integral here minus the integral here, right? It's this area, take away this one. The whole triangle, but then I throw out this bottom piece. And those are the integrals that match those shapes. I have two integrals that both go from 0 to 1, and they're being subtracted. That means I could combine them and make it one integral. And all of a sudden, I think of these again. What if we ignored the x-axis and drew a little rectangle in R and only in R? So if I drew that little rectangle that we were doing for our Riemann sum, it would go something like this. Or like this. Yes? And its top and bottom have nothing to do with the x-axis anymore. Here's the top, and here's the bottom. And that's what I've written right here. Top minus bottom. This is still the height of that rectangle. And the area of a rectangle is height times width. This is the same integral. This is the same area. But I don't have to think of the x-axis as being involved in it. This even makes more sense when I think of problems we already did, where we had part of the curve go under the x-axis. I thought of the x-axis on top and the curve on the bottom, and that's what made that a negative behavior, right? Area underneath was minus because I was thinking of the area under the curve, but it's the other wrong way around. Top and bottom are backwards. I want to think of this in general. If I have some region and it's got a boundary that is a curve on the top and a boundary that's a curve on the bottom, then the area of this region is the integral from a to b of f of x minus g of x dx. Anytime I have a region with a curve on the top and a curve on the bottom, that's all I need. I need the height between them. I just need to know which is top and which is bottom. Here I've given you the description of the region by saying it's got these boundaries. Y equals e to the x, that's a curve. Y equals x, that's another curve. X equals 0, x equals 2, those are numbers. But they also describe vertical lines. So I've got 4 sides to my region right here. And that means I can figure out which one's which, and then I can write an integral. Since these are the vertical lines, that's going to be a left edge and a right edge. Up here, the left and the right edge give me the limits of my integral. So I know right away to start that in order to compute this area, I'm going to do an integral from 0 to 2. Now I just need to know which curve is on top, which curve is on the bottom. So I can set up f and g as I've written them up there. I don't actually tend to think of them as f of g. I tend to think of them literally as top function, bottom function. Which of these two is top? E to the x or x? Between 0 and 2. There are 2 different ways to find out. One, draw me a graph. You have a graphing device. Pull out your graphing calculators. Tell me what this picture looks like. Or pick a number between 0 and 2 and plug it in and figure out which one's bigger. But that makes an assumption that one graph is always on top and one graph is always on the bottom. In this case, that happens to be true. I know that the graph y equals x is a line. Another graph y equals e to the x curves up. That's our exponential equation. And e to the x is always above the line y equals x. those of you who have taken or will take anything in discrete math or complexity, big O of e to the x is much bigger than big O of x. So that one's on top. And that means I have top minus bottom. There we go. I find it helpful to draw the rectangle. It is not required, but it certainly helps me to picture what I've done. Actually, I don't even draw a rectangle most of the time. I just draw a little line. The width of my pen stroke is wide enough to think about dx as a width. But now I know how to do this integral, and that means I know how to compute this area, right? The antiderivative of e to the x. Great. The antiderivative of x. Exactly. 1/2 x squared. And then we go from 0 to 2. So I plug in 2. I plug in 0. E squared, I'm just going to leave as e squared because I don't know what that number is and it's ugly. 1/2 of 2 squared, 1/2 of 4, that's 2. Minus e to the 0, though. E to the 0 is nice. What's e to the 0? Yay. E to the 0 is 1. 1/2 0 squared is 0. Okay. So I get e squared minus 3. I'm not even going to bother to come up with a decimal. You are welcome to, but I'm not going to bother at this point. Questions? Same question. Again, I think picture helps. So draw a picture. Oh, wait a second. I'm going from -2 to 0. So this time, I'm on the left side. That's okay. If I graph y equals x squared, that's the parabola we've been using before, right? So I know that that's going to go like that, more or less. Kind of wiggled there at the end, but I'll live with that. I know it actually keeps going, but I only need the part between -2 and 0. What about 8 minus x squared? Going down. The x squared is a negative, and the y-intercept is 8. Oh, this one's going up, this one's coming down. They're going to cross somewhere, right? 8 minus x squared equals x squared. Means 8 is equal to 2x squared. Divide by 2. Oh, I get x squared equals 4. That means they cross at exactly -2. Hey, look at that. They match up right there. And again, I know this graph continues, but I don't care about that. I only care about the part here between -2 and 0. Again, I'm going to draw the little rectangle in the middle there. And I would like you to set up an integral for me. Integral from where to where of what? -2 to 0 are my bounds in X. Great. What about the integrand? What am I integrating? I'm going to put these parentheses in just for the hell of it, but it's top minus bottom. Exactly like I've indicated right here. Great. That simplifies to 8 minus 2x squared. And I'm good to go. I know how to integrate this. So I get the antiderivative of 8 and the antiderivative of 2x squared. I plug in 0, I plug in -2, and I subtract. When I plug in 0, that whole thing is 0. When I plug in -2, -2 times 8 is -16, and -2 cubed is -8. I have to keep the sign straight here. This whole piece is 0. Minus. All right, wait a minute. Negative times a negative here becomes a plus. I get -16 plus 16 over 3. There's another minus sign outside, so I can move that minus sign in, making this 16 minus 16 over 3, or 10.66666, repeating as many times as you want, 32 over 3. Questions? I am going to change this problem just the tiniest bit and ask you to do it again. I changed the x values. Again, I believe a picture will help. So make me a sketch. Okay, wait a second. Y equals x squared between 0 and 3. I know that goes like that. But that goes all the way up to a height of 9. And this curve starts at 8 and comes down. And what's more, we already know where these curves cross. These two curves actually cross here. But I want to include that area. Uh-oh. This really isn't one area. This is two. And the problem I have is that which curve is on top changes. So instead of writing one integral that goes from 0 to 3, I actually have to write two integrals. One that goes from 0 to 2, and one that goes from 2 to 3. And I have to write them both with top minus bottom. So I have to know, and this is why I said I made an assumption earlier, I have to know which curve is on top and which curve is on bottom the whole way through, as opposed to just at one point. So really, I'm going to do this like this. An integral for A1 plus an integral for A2. If I only did one integral, then one of these two pieces would be counted as negative, because what was on top in the left region becomes the bottom in the right region. That's going to change the sign. So let's go back and figure out top versus bottom in region 1, top versus bottom in region 2. Which curve is on top for the first area? So that's going to give me 8 minus x squared minus another x squared. But over here in the second region, x squared is on top. And this is why I keep putting in those parentheses, because here I have to distribute that minus sign. Here I'm going to get 8 minus 2x squared. Here I'm going to get 2x squared minus 8. I have to distribute the minus sign. That makes the 8 negative, makes the second x squared positive. And now I'm in the same boat I was before, and I know how to do these integrals. I know the antiderivatives, and I can plug numbers. I will also tell you that sometimes you can cheat. So wait a minute. You only gave me two pieces. How do I get four boundaries with only two pieces? Let's make a picture. A graph's going to help here. When I graph this, standard window, x cubed minus x, the sine of pi. Aha. Look at what's going on in the middle there. I'm going to zoom in a bit. I have a bounded region. I have another bounded region. So I get a left and a right because these curves cross each other. 3 times, not just twice. So I got to do 2 integrals. I got to do the integral for the left region. I got to do the integral for the right region. But wait, there's more. What sort of symmetry does this picture show me? Well, it was reflected across the x-axis, then what would be up here is down here. But what's up here is not down here. These two shapes are not the same. It is reflected, but it's reflected through the origin. What's up here is down here. It goes diagonally this way. We gave that a name. It was in the last section, section 5.5, when we talked about symmetry. This sort of symmetry is odd symmetry. And the fact that these are all odd powers and this is an odd function is what helps me make the idea that this area up here should be exactly the same as this area down here. So instead of doing 2 integrals, I really do one of them, multiply by 2. Now I just need to know where things cross. Since I have this picture, second, calculate intersection. And I think they cross over there-ish. Click one curve, click the second curve, get close to where I think they cross. They cross where x equals 1. They also cross at 0. So if I want to do this right-hand region, it's the integral from 0 to 1. But if I want to get the left one as well for free, you need to multiply by 2. Now I just need to know which one's the top, which one's the bottom. On this piece here, which one's the top? Exactly, that's my sine curve. This is where if you have the newer version of the calculator, it shows you things in color, it'd be easier to tell. I don't have color on this one, but I can hit the trace button and I say, oh, that's the cubic equation, that's the bottom, and that's the top. Okay, now I know which one is which. Here's another case where having that set of parentheses helps. because I see that I have to distribute that minus sign again. Now, the integral of x cubed. What's the antiderivative there? Power rule time. Of x to the third, what's its antiderivative? Great. X to the fourth over 4. Antiderivative of x. Ah. Let me do that over here. This is where I'm going to use the fundamental theorem of calculus part 2, which says what I need to do is an antiderivative first, and then I can put in the two pieces. But how do I do that antiderivative? Because that's not sine of x. That's sine of stuff. Rattle, 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 rattle. What do I do when I see sine of stuff? Chain rule. I'm doing an antiderivative, so that means I got to use that substitution idea. Chain rule tells me I'd be doing a u substitution here. And so this is the ugly stuff on the inside. U equals number x. So what's du? What's the derivative of number x? It's just number, so it's pi. Oh, wait a minute. I get the dx there, right? Do I have a pi next to my dx? Nope. So this becomes the integral of sine of u 1 over pi du. The 1 over pi comes out front. What's the antiderivative of sine? Because the derivative sign is cosine. I've got to go the other way around. That means I get the extra minus sign. Hey, that's going to go over here. Negative 1 over pi cosine u. But u is pi x. And now I can plug in a 0 and a 1. And when I'm finished, I can multiply that whole thing by 2. Ta! Doesn't that just suck? I needed another technique in the midst of doing this area between my two curves. Now, I will also tell you that sometimes top and bottom, left and right, change roles. This is a problem because y squared equals, I can't graph that here. I can't graph a y squared on my calculator. The only things I can graph on my calculator are things I can write y equals. So I can't graph this equation on here the way it's written right at the moment. I could split this up into two different equations. And I could graph those, or I could go back to my pre-calculus class. Now, because x squared is a parabola that goes this way, y squared is a parabola that goes this way. It goes sideways. Hey, wait a minute, that's a square root curve. Okay. This is a negative square root curve. I get that. But then I got this curve, y equals x minus 1. This has got to go out further. This is the region I want. Here's the problem. If I want to do this with a top and a bottom, there's a line here where the top and the bottom are both the parts of the parabola. And over here, the top and the bottom are parabola and line. That's going to suck. But turn your head sideways. I'll cheat. I'll turn the paper. A top and a bottom. A left and a right. Only this is the positive direction for y. So left and right. But that means I can think of this as having an x on the right and an x on the left, and those are the curved sides. And then the top and the bottom are y values. Y equals a number in both cases. And I can find out what that number is. Y equals x minus 1 and y squared equals 2x plus 6. Means I can put that in there. And I can solve. Minus 5 equals 0. So that's x plus 1, x minus 5. X equals 1, x equals 5. But if that's x equals 1 and x equals 5, that means that y is equal to, x equals negative 1. Y is equal to negative 2. And x is equal to, x equal to 5, y is equal to 4. So I can think of drawing my rectangle sideways. Instead of drawing that rectangle this way, I draw it this way. And now the top is here and the bottom is there. And that means this integral's thickness goes along the y-axis. Instead of the x-axis, I'm going to do an integral dy instead of dx. It's the exact same idea. I just turned the picture 90 degrees. I need to rewrite this equation. This equation is the right equation. That's the line. So I write it x equals y plus 1. I need to do the same thing with this equation and write it as x equals. So this equation becomes y squared minus 6 is 2x, or x is 1/2 y squared minus 3. And then I integrate from negative 2 to 4. And I build up my slices going up and down instead of going from left to right. My little rectangle slice doesn't go this way, it goes this way. There is a nicer illustration than mine in the textbook on page 440 that shows you the problem doing it up and down and shows you the easier version left to right. I'm going to keep using these ideas. I'm going to draw more pictures like this. I'm going to take this exact same idea and use it to build solid objects 2. Because if I think of slicing this up in areas, think of a slice of bread. I'll bring in a loaf of bread tomorrow. We'll talk about it then. I will see you all tomorrow. Have a wonderful rest of your day.